Today, we are learning about power. In physics and in science in general, we call the rate at which work is done power. So when we're talking about, something's like pulling power, we're talking about how quickly can it do that work of pulling it across this distance. A more general definition might be the rate at which energy is transferred, because remember that anytime we're doing work, we're just transferring energy from one object to another. So how quickly can that energy be transferred? That's what we're defining as power. The equation we will use is power is equal to work over a time interval. So pretty straightforward. W is the work done on an object, and change in T is the time interval over which that work is done. Wait. If we substitute the equation that we have for work into the equation for power, then we get an equation that looks like this. We know our equation is work equals force times distance. And we can sub that in and we'll wind up with power is equal to work over time, so we could substitute it in as power is equal to force times distance all over time. And since we know that distance over time is just speed, we can simplify the equation into power is equal to force times speed. F, of course, is force, and V is, of course, speed of object. The SI unit for power is the watt, which we use a capital W to mean. That should say watt, not was. That's a typo. 1 watt is 1 joule per second. And horsepower, which is another unit that you will sometimes see people measure work in, is abbreviated HP, and 1 horsepower is equal to approximately 746 watts. So, our example problem. We have a 193 kilogram curtain, and that curtain needs to be raised 7.5 meters at a constant speed in as close to 5 seconds as possible. So this is a situation where, like, you're trying to raise a curtain backdrop on a play.
Gotcha.
Right? Gotta move it quickly. The power ratings for the 3 motors that are commonly used to do this job are listed as 1 kilowatt, 3.5 kilowatts, and 5.5 kilowatts. Which of these motors would be best suited for the job? So we don't want underpowered and we don't want overpowered. We want the one...
don't want it to go wee!
The Goldilocks zone, basically. We want the one that's going to do the job without doing it too quickly and causing other problems, or doing it too slowly and interfering with the scenes on stage. Okay. So what you'll need to do, basically, is calculate the work that needs done, and then you'll figure out how you have the time that you want it done, right, and then you'll figure out what wattage you would need and compare it to the 3 wattages we have, bearing in mind that the wattages have been given to us in kilowatts and not watts. So
Gotcha. So we'd have to
paying attention to that. So we can use our equation for power. We know power is work over change in time, and we know that we can also write that as force times distance over change in time, right? Mm-hmm. And then we also know that force is equal to mass times acceleration. And since in this case we're talking about the force required to lift that object, the acceleration would be the acceleration due to gravity. So we could really actually even write this as mass times gravity times distance over change in time. And if we plug all those things in, we have the 193 kilograms times the 9.81 meters per second squared times the 7.5 meters that it needs to go, all divided by the 5.0 seconds needed to take it in. We should come out with a power equivalent to 2.8
Yes.
times 10 to the third watts. Also could be written as 2.8 kilowatts. And so the closest one to this would in fact be the 3.5 kilowatt motor,
Yay!
meaning the 1 kilowatt motor wouldn't lift it in time, and the 5.5 kilowatt motor would lift it way too fast. So,
Hey, go flying.
so that's the end of the notes on power.